Hello, hello, hello. The day has come that I'm going to discuss with you the solution to this crazy tunnel, this imaginary tunnel that people imagine they might dig someday. The tunnel goes from Oslo to Honolulu straight through the earth. It's a straight line. The tunnel is completely frictionless and we ignore air drag. And then we want to know how long it would take for a vehicle that enters the tunnel here with 0 speed to reach Honolulu. And it will reach Honolulu also at 0 speed. It will increase its speed and then it will later decrease its speed and it will come to a halt again in Honolulu. We can calculate this time if we make some simplifying assumptions. One is that the Earth is a perfect sphere. That's very close to the truth. Very close. Second, which is not so close to the truth, that the density of the Earth is the same everywhere. Alright, we agreed on rounding off some numbers because I'm really not interested in 4, 5, 6 digit precisions. I want to know the time that it takes for a vehicle, and you are of course in the vehicle, to go from Oslo to Honolulu. And I want to know that time to an accuracy maybe of a minute or so. And so we will all use for the Earth a radius 6.4 times 10 to the 3 kilometers. This is not in SI units. This is the gravitational constant. 6.7 times 10 to the minus 11, that is SI units. And we will take for the mass of the Earth 6.0 times 10 to the 24 kilograms. And in case you need pi, we will use 3.14. And then I did something very naughty. I gave you the position of Oslo and the position of Honolulu in terms of latitude and longitude. But you don't need it. Yeah, you really don't need it. Okay, so let's now look at the solution, which is actually not very difficult. Okay, so now I draw the tunnel horizontally. I could have drawn it like this or like that, doesn't matter how I draw it, but I rotate the Earth in such a way that this is Oslo and this is Honolulu. And this cross-section through the Earth includes the center of the Earth. That's very important. So from here to Oslo is the radius of the Earth. From here to Honolulu is also the radius of the Earth. And this is the tunnel. I draw a line from the center of the Earth perpendicular to the tunnel. And I call that location where it intersects with the tunnel, I call that x equals 0. In this direction along the tunnel I call positive x, and in this direction would be negative x then. You, in your vehicle, have a mass, that includes you and the vehicle, of little m. And at one point in time, you are at this location x. You're x away from this point. The question now is, what is the gravitational force on you? If from the center of the Earth to you, the radius is little r, lowercase r, then the mass that attracts you is only the mass that is inside the sphere with radius little r. If you have any difficulties to digest that, it took also Newton some time. The story has it that it took Newton about 40 years. There is an equivalence in electricity and magnetism which we call Gauss' law, but I will not go into that parallel any further. But it's key, therefore, that you understand, or do your homework on it, that the mass of the Earth that attracts you when you are there is little r cubed divided by capital R cubed times the mass m. So that's the sphere, that's the mass of the sphere with radius little r. If you didn't get that right, then of course everything falls apart. So now I apply Newton's universal law of gravity and I calculate the gravitational force on you in this direction, pointing towards the Earth. This is Newton's universal law of gravity. This m little r is this value now. It's not capital M, it's less. And so I substitute for this m little r, I substitute in there this value. So I get capital M back into my equation. However, since there is no friction anywhere in the tunnel, the normal force on you and your vehicle are irrelevant because there is no friction. So we don't worry about the normal force. The only force that matters and the only force that drives you is the component along the tunnel of that gravitational force. So this is that gravitational force, if you can see red, and this is the component along the tunnel. And so that component is of course the magnitude of the gravitational force in this direction times the cosine of this angle here. And that cosine is x divided by little r. And so if you get out m of r and replace that by capital M, you find this result. Notice that I put a minus sign here. And I do that because you will shortly see that that's very important, that you realize that if x is positive, the force is in this direction, f of x is in this direction. And later when the object is here, when x is negative, that force is in this direction. So the force opposes always the direction of where you are relative to this point 0. Remember when you have a spring, that the spring force is always opposing the direction in which you stretch the spring. We call that a restoring force. So the minus sign is crucial. You tell me what x is. If it's positive, then the force is in this direction. If x is negative, then fx is in this direction. Fx is of course the mass of the vehicle and you times a, the acceleration along the tunnel. And that is of course x double dot. That is d2x dt squared. So here you see really F equals ma. So now I replace this f of x by mx double dot. I rearrange the math a little bit of massaging, and I come up with this equation. And when I see that equation, I almost get tears in my eyes. I can dream of that equation. It's one of the most beautiful equations in physics of all time. That differential equation is extremely similar to the differential equation of a spring that you stretch a distance x. It's a simple harmonic oscillation. And the solution to that differential equation is that x at a particular moment in time t that you may choose is x maximum. This distance would be x maximum times the cosine of omega t. And omega, we often call that the angular frequency. So this is the solution to this differential equation. If you don't believe it, substitute this in here and you will see that that equation is satisfied. So that means that omega is the square root of this constant. If you don't remember that, well, brush up on simple harmonic motions. But we know, of course, that omega is 2 pi divided by capital T, where capital T is the time in seconds to make one complete oscillation. Oslo, Honolulu, back to Oslo. And here you see that time. What an amazing result! That time is the same for any tunnel through the Earth, no matter how long that tunnel is. If I have one here, or one there, or one there, in all cases, the time for a complete oscillation back and forth is the same. So now you can calculate what the time is for one complete oscillation. And therefore the time to go from Oslo to Honolulu and then get out of your vehicle is half of that. I didn't even write that down. But that time would be pi here rather than 2 pi. So let's now look at the results. Yeah, you should be able to see this. So we agreed to round off the radius of the Earth, 6.4 times 10 to the third kilometers. The mass of the Earth, we agreed on this number, and we agreed on the gravitational constant. If I substitute these results into our equation for capital T, which is the time for a round trip, then I find so many seconds, a number that I already remembered from my high school days, 84.5 minutes. I always remember something like roughly 85 minutes. So, it's pretty fast. So you make it to Honolulu in about 43 minutes. It's half of this time. A plane would take about 14 hours. So in that sense, apart from the fact that you will never survive that travel through the tunnel, that's a detail, you would make it, your body would make it in about 43 minutes. Now comes something that may not surprise many of you, but maybe some. The time to go back and forth in the tunnel, in any tunnel that you dig through the Earth, of course, again, assuming frictionless, no air drag, and assuming that the density of the Earth is the same everywhere. I repeat that because that's an assumption I made. So the time for a satellite to go around the Earth in a circular orbit is the same equation that we derived for the time to go back and forth in the tunnel. The only difference is that you cannot have a satellite, say 1 kilometer above the Earth's surface, because there's an atmosphere. So you always have to make capital R in that equation, how about 300 or 400 kilometers larger than the radius of the Earth. But apart from that, isn't it amazing that it is exactly the same physics? If you have a satellite in circular orbit around the Earth and your mass is little m and your speed in orbit is v, and the radius of your orbit around the center of the Earth is capital R, then the centripetal force on you must be identical to the gravitational force on you. Both are perpendicular than the direction of your motion, perpendicular to your circular orbit. And you know, of course, that the speed in your circular orbit is 2 pi r divided by the time that it takes to go around the Earth. This is the distance that you travel, and this is the time that it takes. So I take this v, substitute that in here, I get rid of my little m. That means all satellites at distance r from the center, regardless of their mass, will all go around the Earth in the same amount of time, and this is then the answer. And that's exactly the answer we found for the tunnel. But I repeat myself, with the tunnel, this r was the radius of the Earth. Here you can put in the radius of the Earth, but no satellite could be there because of the Earth's atmosphere. So any satellite that survives has to have a radius which is a little bit more, like 300 or 400 kilometers more than the radius of the Earth. Let's go to the ISS, the International Space Station. It's about 400 kilometers above the surface of the Earth. So the 6.4 becomes 6.8. So I put 6.8 times 10 to the 6, because I need SI units, in this equation, and out pops the time that it takes the ISS to go around the Earth. About 93 minutes. You can look that up on the web, you will see. That's within a tenth of a minute, exactly the right value. You don't expect us to be that accurate, of course, within a tenth of a minute, because we've rounded off numbers. So typically what you should remember, and what probably most of you do, and I certainly did when I was in high school, and when I wanted to watch at night satellites, the light of satellites, reflections of the sun, it takes them about 1.5 hours in orbit to go around. We call that a near-Earth orbit. And near-Earth then always means 200, 300, 400, 500, 600 kilometers or so. If you're going much, much further than that, suppose you go 10,000 kilometers, then the period will increase accordingly, because R goes up. All right, I thought you would like this problem, and some of you may be mad at me because the location of Oslo and the location of Honolulu have no effect of the outcome. I could have asked you what is the maximum speed of your vehicle. Then of course you would have to calculate the x maximum. So then you would have to calculate the distance in meters or kilometers from x equals 0 to Oslo. But I was not too much interested in that. The longer your tunnel is, the higher will be your speed when you reach x equals 0. In all cases, your speed will be 0 where you enter and 0 where you get out of the tunnel. But the longer the tunnel, the larger the speed when x equals 0. And that makes up exactly for the fact that the time that it takes for you is the same. That's independent of the length of the tunnel. Well, I hope you survived this and that you still want to be friends with me. Many of you, I'm sure, have seen this problem in high school, and you can also find the answer on the web. Almost any problem that I give you, somewhere you can find it on the web. Have a nice day and take care.